Welcome viewers to the third segment of the sixth lecture of online series of lectures on Introduction to Category Theory. I stated lemma 1 in the previous segment, which states about the uniqueness and existence, the existence and uniqueness of this arrow from the disjoint union of x and y to this set A. Okay? This arrow is precisely this map from this set to the set A. Okay? So we need to prove it. So let me go over the proof. I leave the diagram here that I might need you during the proof. Proof. Suppose f and g are as given. So, for the moment, we denote this function with L to provide a function L from disjoint union of x and y to A is equivalent to providing a unique element Ln in A for each m in the disjoint union of x and y. Okay? So for each m here, we need a unique element Ln in A, and then this L will be well defined. We need such a function for which so this function needs to be figured out such that both the left hand triangle and the right hand triangle in the diagram commute, for which the left and right triangles commute separately. Okay? That is, see, if you take the left triangle, we're denoting it with L now. Okay? So if the left triangle commutes, we must have L composed with L composed. So the two paths here from x to A, one path is this one and the other one is this one. So this path is L composed with I1, and that must be equal to this path F, and the other one is L composed with I2 is equal to G. They need to be satisfied in order for the diagram to commute. Now, there are a few things that we need to consider. Each element and in the disjoint union of x and y is either I1x, there is I1x. So if x is an element of big X, I1x will be here. So any element here is either of I1x or I2x. I2x. Here. Sorry, I2y. Excuse me. Where y is an element in this big Y. For x being in X or y being in big Y, and can't be of both forms, as we know from the definition of disjoint union of two sets. Okay? Okay. Now, see that this is something that we need to satisfy. So we want L composed with I1 acting on X to be equal to f of X for a given X, small x in this big X. Okay? This is what we need. And this is equivalent to L M is equal to f of X if M is equal to I1x. Okay? Again, L composed with I2 acting on Y is equal to G of Y. Okay? This is what we need for the diagram to commute. And this will tell us that L of M is equal to GY if M is equal to I2Y. Right? So M is either I1x or I2y. There is no other option for M from the definition of the disjoint union of two sets. So we assign, so how can we define L in a well-defined fashion? So we assign, here is the definition. We assign L M is equal to Fx. We assign Ln to be equal to Fx if M is equal to I1x and Ln is equal to Gy if M is equal to I2y. So this way we can define L so that the entire diagram commutes. Okay? We sort of did a back calculation to check what will be a very nice definition for L. And this is the best definition for L for which everything will commute, and hence this proves the existence of this function. Similarly, you can prove the uniqueness as well. So the above statement, this assignment is necessary and sufficient to make all relevant diagrams commute. Okay? So this is the proof. Alright. Now we get back to the example of the ONO that we provided for sits in an airplane. Let me go back to the example of that O-log. Okay. And study the universal property of coproduct in the setting of that example. Okay? Example. Airplane 6, continue. Okay. So let me draw the figure first. So what did we have initially? We had this coproduct here, which we denoted by X, this joint union Y, a seat in an airplane. If you go back to the to previous segments, you will find it there. A seat in an airplane, a seat in an airplane, and there was this canonical inclusion of this type here. Our first class seat in an airplane, our first class seat in an airplane, and to the left of the diagram I have another inclusion map, an economy class sit in an airplane, sit in an airplane. Okay. We denoted this with X and we denoted this type with Y. This was the O that we had earlier. Okay. So now there is another type here which we label as a dollar figure, which is relevant to force price of the seat. A dollar figure, say 50,000 US dollars, so I don't know, 25 US dollars, something like that. Which will of course be instances of this type, okay? Not this thing, exactly. Right? So there is an arrow here, which is labeled as hazard's price. So it tells you that an economy class seat in an airplane has as price a dollar figure. And the first class seat in an airplane has as price also, has as price a dollar figure. Okay? So there exists a unique arrow from this whole product to a dollar figure. Okay? So the universal property of coproduct tells you this obvious fact that you can understand intuitively immediately. Let me write it down here. If we know how economy class seats are priced. In other words, you are given this aspect. You know how this economy class seats are priced in terms of dollar figure. And we know how first class seats are priced. First class seats are priced, and if we know that every seat, and if we know that every seat is either economy class, economy class or first class, of course in the bracket we write but not both, which is obvious in this case, but not both. Because an economy class can never be a first class seat. Okay? Then we automatically know how all seats are priced. All seats are priced. We automatically know how all seats are priced is this unique arrow. Okay? So if we know how economy class seats are priced, and if we know how first class seats are priced, and if we know that any seat is either an economy class seat or a first class seat, then we of course know how any seat is priced. This is an obvious fact, and it comes from the universal property of coproduct. Okay, now I need to discuss finite co-limits in set. Like we discussed finite limits in set in the beginning, we need to discuss finite co-limits in set. And we also need to discuss what it means by pushout. In order to do that, we need some background concepts on equivalence relation and equivalence classes. Okay? So let me get started with equivalence relation. Equivalence relations. Okay? Definition. So I named the definition with equivalence classes. Equivalence classes and equivalence relations and equivalence classes. Equivalence relations comes first. Relations and equivalence classes. Let me remind you of the fact that it is a very important topic to understand what we'll be discussing for the rest of the lecture. Okay, so try to focus on this part very carefully. Let X be a set, simply a set. Okay, an equivalence relation on X and equivalence relation on X is a subset R of the Cartesian product of X with itself. Okay? So an equivalence relation is the subset R of this big set of Cartesian product of X with itself, satisfying the following properties. Satisfying the following properties. Following properties for all x, y, z in big X. Okay? So what's the first property? The first property is called the property of reflexivity. It tells you that all ordered pairs like x comma x should always be in R. Okay. Symmetry, the next property, symmetry. Symmetry tells that if x, y is in the set, then yx will also be in the set and vice versa. So in other words, xy is in R if and only if yx is also in R. Now the final one is called transitivity. If xy is in R and yz is also in R, then of course xz is in R. If R is an equivalence relation, we often write the fact as x is related to y this way, or simply x is equivalent to y, dropping that R sign when that is obvious. To mean, what does it mean? To mean x comma y is in the subset of x product x. Example. Now I give you an example. Example of equivalence relation. We all know that this boldface Z denote the set of integers. Define a relation R, which is of course a subset of Z cross Z. So then we'll say that R is a relation on Z. Okay. And this is defined by this subset. So all the ordered pairs satisfying the following property will be in R. And what is that property? There exists n in the set of integers such that x plus 7n is equal to y. Right? And then say that if this happens to be the case between x and y, we'll say that x comma y is in this subset of z cross z. Is it an equivalence relation? Now the question is, so I'm going to prove that then R is an equivalence relation. Okay, let's prove it. I mean, there's nothing to prove. We check, we verify that R is indeed a relation, an equivalence relation. Because, first, x plus 7 times 0 is equal to x. So, since 0 is in the set of integers, x is related to itself. Proving that x comma x is in R. So it proves that this relation R is reflexive. Second, okay, let's say that there exists an n for which x plus 7n is equal to y. It tells you that x comma y is also in R. Okay? X comma y is in R. It tells you that x comma y is in R. Okay? And you see that by taking y on the other side, or by keeping y on this side and taking 7n to the other side, we immediately see that y plus 7 times minus n is equal to x, and this tells that y comma x is also in R, right? So that we have verified that R is symmetric. Thirdly, if x plus 7 times n is equal to y, so I'm claiming that xy is in R, and y plus 7 times n is equal to z. So another claim is that y comma z is also in R. Together, okay, but with n and both being integers, okay. So if you substitute the value of y from here to here, you end up with the following equality: x plus 7 times n is equal to minus 7 times n plus z, right? Resulting in x plus 7 times m plus n is equal to z. Since m and n are both integers, m plus n is also an integer, signifying that x comma z, this ordered pair, should also be in R, which proves that R is also transitive. Okay? So this will prove that R is indeed an equivalence relation. Okay, good. Now I need to say, say a few words about equivalence classes. That is a derived concept from this definition of equivalence relation. These are very important features. We need to understand them very well to understand what it means by pushout and also the idea of coequalizers. Okay? So now, a few words on equivalence classes. Okay. Suppose twiddle is an equivalence relation. Well, it's a bit abuse of the terminology because we say that equivalence relation is a subset, but by equivalence relation now I mean this relation. Okay, so this is an equivalence relation on X. On X, the quotient of X by that equivalence relation twiddle denoted by X slash twiddle. So this was the set. X was initially a set. X is the set that we started with. And then on X we find an equivalence relation given by this twiddle. And we know what it means by an equivalence relation. It needs to satisfy certain properties called reflexivity, symmetry, and transitivity. So suppose that this twiddle satisfies all those three properties, so that this twiddle is an equivalence relation on X, and then we define. So we are going to understand the concept of this quotient of X, which we are going to denote by this X slash twiddle. And this is again a set. Is the set of equivalence classes of twiddle. Equivalence classes of twiddle. Okay, so it will be much clearer when we study this notion in the context of the previous example that I'm going to do in a short while. But before that, I need to say a few things about this equivalence classes. By definition, there is exactly one equivalence class A, one equivalence class A such that X is in A. Meaning that you cannot have two equivalence class containing the same element of X. So it's called a partition. So you create a partition of X such that every element is containing exactly one equivalence class. Alright? We'll see that in the context of the previous example in a while. Alright. So since this is the situation, we have a well-defined function. We have a well-defined function called a quotient function from the set to the quotient set, called the quotient function. This function is called the quotient function. Okay, so it's reasonable to define a function like this since each element of A, well, why am I calling it A? That is the problem. Well, yes, so A is an element from here. So A belongs. Sorry. So each element of X is containing exactly one element here, which is an equivalence class. And since this is the case, it's reasonable to define this quotient function this way. Okay. All right. So we say that X is mapped to the equivalence class containing X. Okay. This is how we define Q in terms of the elements. In terms of the elements of the set. Okay. X is an element of X, and this X inside the brackets, square bracket, is an element of this quotient set. Okay, so okay. Okay, now in terms of the example, let us think about this. This idea of equivalence classes in the context of the example that we gave earlier. Okay. So yes, so, let me erase not everything. I want to keep this part. Let me start writing out and see if we have enough space. For the example provided earlier, recall that what was the equivalence relation? The equivalence relation was R was the collection of all the ordered pairs for which there exists an integer such that x plus 7n is equal to 1. Okay. So let us verify immediately that -14, -7, 0, 7, 14, and keeps going on forever to the positive infinity. These are collection of integers, these integers precisely, which are 7 distance apart from each other, are all equivalent to each other. The elements here, all the elements here in this set are equivalent to each other because they satisfy this condition. Okay? 7 is -7 is equivalent to 7 since they are difference, it can be written as 7 times n per some n. Okay? So they belong to the same class because all the elements here are equivalent to each other in using this definition. This is one equivalence class. Okay. All right. Next, take another equivalence class. Let's take -30. Just adding 1 to all the elements, we get -13 by adding 1 to -14, and then by adding 1 to -7 we get -6, and then adding 1 to 0 we get 1, 8, and then we have 15, goes on like that. See that 15 is equivalent to 8 because 15 minus 8 is divisible by 7. minus 6 is equivalent to 8, since their difference minus 14 is divisible by 7 as well. So they form an equivalence class as well. But if you choose one element from here and one element from there, the difference is not going to be divisible by 7, because the difference is 1 here between 7 and 8, which is not divisible by 7. Okay? Or if you choose minus 7 and 8, the difference is 15, and 15 is not divisible by 7. So they don't belong to the same class. So what is another class? By adding everything here to 1, we get minus 12 here, and 5 here, 2 here, 9 here, 16 here, and goes on forever. So this is the third class. Now we can form the fourth class, which is minus 11, 6, 3, 10, 17, and then comes minus 10, then we have 7, we have 4, I'm not sure if I'm doing it right. I think so. Well, I think I'm making a mistake from here on. So this should be minus 5, okay? And this should be minus 6, right? No, it should be minus 4. Sorry for that mistake. Minus 4. Now it's fine. And this is minus 10. And then we have minus 4 plus 1, minus 3. And then I have this by 4, and 11, and 18, and goes on forever. Now it's fine, I guess. Minus 12, minus 5, minus 11, minus 4. The difference is always 7, as you can see. The difference is 7. The difference is 7. And 1, 2, 3, 4, 5. That is the sixth one. The sixth one is, I'm writing down all the equivalence classes in this case. This is, if you add 1 to it, it's going to be minus 9. Then minus 2. And then you have 5. And then you have 12. And then you have 19. Goes on like that. And finally, we have minus 8. Okay. And then you have minus 1. And then you have 6, 13, 20. And if you add 1 further here, you will get back to here. See that you will have minus 7, then you will have 0, then you will have 7, you will have 14, and goes on like that. So you get back to the same class. So there are precisely 7 equivalence classes. And we can denote these 7 equivalence classes as follows. By 0, underbar 0, underbar 1, underbar 2, underbar 3, underbar 4, underbar 5, and underbar 6. Okay? So it means that if you pick up any element from this set arbitrarily, and if you divide that element by 7, you will have a remainder of 1. Let's say if you choose 15, you divide 15 by 7, you end up with 1. If you have 17, you divide by 7, you have a remainder of 2. Okay? If you pick up 17, you divide by 7, you have a remainder of 3. Okay? You pick up 18 or 11, and divide by 7, you have remainder 4, and so on. Okay? So now, what is the quotient function in this case, in this example? See that yeah. So this is pretty much it. So so the x in this case was the set of integers, right? And the set z slash twiddle is precisely this set with 7 elements: underbar 0, underbar 1, underbar 2, underbar 3, underbar 4, underbar 5, underbar 6. Okay? So that under this quotient map, an integer goes to the equivalence class that it belongs to. Right? So minus 7 is an element from this set of integers, and it belongs to this equivalence class. So if you choose 2 elements or many elements which all belong to this set of integers and belong to the same class, they are projected to the class 0 here. Okay? Which means that it is not an injective map, although it's surjective. So the quotient map is a surjective map, but it's not an injective map. Okay, I think we are done with what we needed to know about equivalence relation and equivalence classes and how to do partition on a set like this using the equivalence relation. Now we move on to the concept of pushout. Pushout. Okay, so I want you to recall the definition of disjoint union of 2 sets given by this notation. Okay, this was the notation of the disjoint union of 2 sets. If you remember it precisely, it was written like this. It's the ordered pair x with 0. 0 stands for the index attached to the first set, and 1 is the index attached to the second set. So, for the first set, the elements in the whole disjoint union of these 2 sets is x comma 0, where x belongs to x, and the standard union of y comma 1, where y belongs to the other set y. Okay? Right. So this is the disjoint union of these 2 sets. And now we have this following diagram. Let me draw a diagram. We have 3 sets, w, x, and y, and we have 2 functions. One from w to x and other one from w to y. So this diagram tells you why we calling it push out, like w is pushed out to x, and so is w is pushed. So here also downwards w is pushed out to y. Okay. The push out of f from w to x and g from w to y, also called fiber sum. It has a different name, also called a fiber sum, analogous to what we studied during fiber product, okay, called fiber sum. So you remember that we had this notion of product for two sets, and we had this notion of fiber product of x and y over another set z. Now we are having this notion of coproduct, and we'll have something like this called fiber sum. It was fiber product, it will be fiber sum, as the name suggests. Okay? So this is the fiber sum. So it is yet to define. I'm going to define it now. Okay? Fiber sum denoted by this notation. So I'm going to define pushout. Okay, is defined as the quotient of this, as the quotient of, we know what it means by quotient function, as the quotient of the coproduct by the least equivalence relation, So if you don't understand the meaning of this, just leave it like that, okay? Because in order to, so it's the finest or least, it's the topological things, we don't need to know these things right now. So it's just just think of it as an equivalence relation, the way I'm defining it right now. So fx, 0 is going to be identified with GW, 1 for all W in W. Okay. So you see that. So we have to, in other words, so let me complete the definition. In other words, this fiber sum of x and y over W is defined as the quotient of this joint union of x and y by some equivalence relation with this equivalence relation on x, this joint union with y is defined by Fw, 0 is identified with Gw, 1 for all W in the. Okay. All right. So you see that in this joint union there are many ordered pairs. Okay. There are many ordered pairs here. So there, you don't put any constraint there. You just put all those set elements there. But now you put further restrictions. You cannot choose. So yeah, you choose all the ordered pairs, but no, not all the ordered pairs are distinct. Some of them are should be chosen to be equivalent. You put more constraints so that there will be lesser elements in the set. So in the final set here. So you identify the elements. So in the original disjoint union, there may be two distinct ordered pairs which have to be identified in this new set. Okay? And the rule is given here. So, okay, so this is the rule. Okay, so I leave it here for the rest of the materials will be discussed in the last segment of this lecture. Okay, so I take a break now. I'll be back soon with the rest of the lecture materials. Thank you.